Hi, welcome to the Professor's Du Bois channel. I'm Professor Corey.
And I'm Professor Victoria. Today we're going to be talking about significant figures, how to count them, why they're important, and how to calculate with them, as well as error as it relates to scientific measurements and laboratory skills, and also accuracy versus precision. So let's get started.
Let's get started.
Okay.
All right, we're going to just start out counting significant figures, and we use this method, the Atlantic-Pacific Method. It's something we didn't create, but we find it to be extremely useful for counting significant figures. So the way we approach this is we'll have a map of the United States, and I'll put a big P there for the Pacific Ocean, which is over on the west coast, and I'll put an A on the east coast. That's the Atlantic Ocean. Except we're not really concerned about the oceans, but that P is going to remind me of decimal present. That's what the P represents, and the A is going to be decimal absent. So how do we apply this? Let's look at this first number up here, this 0.01200. There is a decimal present. So I'm going to start on the west coast of this number. I'm going to start over here. And I'm going to count in this direction. Now, the one simple rule is that you can't start counting until you hit a non-zero number. So decimal present, I'll start over here, and this is a 0, and this is a 0. Here's my first non-zero. So 1, 2, 3, 4. This has 4 sig figs.
Count all of them once you start, even if they are zeros.
The next one is 1200. Decimal absent. There's no decimal here, so I'm going to start on the right-hand side, the east coast of this number, and I'm going to go to the left. I'll start counting at the first non-zero, then I'll count them all. The first non-zero is that number 2, and then there's a 1, so there's 2 sig figs in that number. Notice how this one has a decimal? It's kind of funny. It's 1200 with the decimal point. Well, this is important because this number, it's the same value as the one prior, but look how many significant figures we have. We have a decimal present, so we start over here on the Pacific coast. The first number is not 0, so we count it and everything else, and this one has 4 significant figures.
Works every time.
When we have scientific notation, we aren't concerned with the times 10 to the. Our significant figures are all up in the front. So this is decimal present. The first number is non-zero. This is 4 sig figs. So we do have a much more detailed video going over this method.
Highly recommend.
Now let's kind of get into why do we count these numbers? Like what is this just some, is this just some practice? What?
Something to make you crazy?
Yeah, why are these numbers significant? Maybe that's a good question. Why are they significant?
Right. And what's really important about significant figures, the reason that we have significant figures is to communicate how confident we are in the number. So just like the 1200, we weren't as confident in the 1200 without the decimal. We were much more confident in the 1200 with the decimal. So what does that even mean? So if we're measuring the height of this totally awesome VW bus, and we have this measurement, meter stick kind of thing, ruler on the right hand side. It's very crude, but let's just say we have this measurement tool and it goes from 0 to 10 meters and we want to measure it with that. And that's all we have is that. So if we're going to measure that just to the top of the top of it, maybe come across and we estimate, all I know is it's above 0, it's less than 10. I'm going to say that's 8. So I'm going to say that's 8 meters. Now that was an estimate. The estimated digit, one estimated digit is significant. So that was the best I could do. Someone else looking at that might have said 9. So it's an estimate, but we have one significant digit. Now, if we increase the number of graduations on our, meter stick or our measuring tool. So now we have 1 meter graduations. Now if I bring over the height and I can say, oh, yeah, it's definitely less than 8, but it is greater than 7. So it's 7 point something. So I have 7 is one significant digit, and then I'm going to say, oh, I think that's 7.6. So now I have 2 significant digits. I have more confidence, I'm sure of the first one, and I have an estimate as well. So I have 2 significant digits. So that is a more precise measurement. We're going to talk about accuracy versus precision. And precision is about reproducibility. And with this measurement technique, this measuring stick with greater numbers of graduations, I have a more precise measurement. I have one digit that's definite. It's definitely 7 point something. And then I also have the estimated digit. Now, if we had 10 graduations in between all of these, we could have 3 significant digits. And if we had, if you just keep getting smaller and smaller and smaller, then you have more and more significant digits and you have more reproducibility, more precision.
So I think the key point here is whenever we make a measurement, we use the measurement tool that we have, and the last digit is estimated. Let's put this to chemistry and look at a graduated cylinder. So the graduated cylinder has graduated lines on it. And the first thing I like to do is just kind of orient myself. Like, I'm looking at this, I've got a 25 and a 20. And my water line is between the 20 and the 25. And I'll count these and realize that each of these smaller lines is 1 mil. So if I take a little better close-up image here, I can see that I definitely have more than 21 and less than 22. So I can say with certainty that I have 21, but then I have to estimate that last digit. And I'm going to call it 0.7, 21.7. And that number has 3 sig figs.
Nice. So if there were more graduations, he could get more significant digits, more exact. So we also need to be concerned with calculating with our significant digits. So not only do you need to be able to count them, so you might be presented with a problem that has measurements in it, and the number will give you the number of significant digits that are in there, but then we also calculate with them. So sometimes we do multiplication or division that has one rule, and addition and subtraction has a different one. So when you are presented with a problem and you have to do multiplication or division, you're going to look at all of your numbers and round your answer to the lowest number of significant digits in the question. So if you have 3 different measurements in your question and the lowest number of significant digits is 2, then you do your multiplication and then round to 2 significant digits of your answer. If you're doing addition or subtraction, then you will look at all of your numbers and round to the lowest number of decimal places. And we're going to show you examples of each of these. Now, exact numbers do not limit significant figures. In previous lectures, we talked about conversion factors. So if you have 1 gram is 1,000 milligrams, those are exact numbers. That's not a measurement. Only your measurements are have significant figures.
So here's an example. They want to know the density. Notice how density keeps coming up. This is an important concept, density. So we want to calculate the density to the correct number of significant figures. We have a mass, we have a volume, and this looks like a multiple choice question. All the units are in grams per liter, and I have a mass in grams, and I have a volume in liters. So I'm going to just start this by writing my 2,500 grams, and I'm going to divide by 4.550 liters. Now, when I do this in my calculator, I get a rather large number, and I'm going to write the whole thing right out, well, most of it. And then I'm going to decide how many significant figures my answer should have. So what I do is I go back to my measurements in the question. I have a volume measurement, and this has a decimal present, so I have 4 sig figs here, and I have a mass measurement that only has 2 sig figs. So since the mass only has 2, that's going to limit this answer to 2 sig figs. Now there's a couple ways I can do this. I can write this as 550, gram per liter. Forgot my units up here. That's bad. And the other thing I could do is I could go 5.50 or
5.5. No zero. Right? Because
two
5.50. Yeah, two significant figures.
Sometimes I make mistakes. 5.5 times.
That's why we have each other.
10 to the 2 gram per liter. Now, the answer to this question would be number 3, because they didn't show it in scientific notation. But that scientific notation is pretty handy sometimes when you get in one of those binds with significant figures.
So here's another example. What is the total mass? So we need to add these together. So if we add, one sample is 3.5 grams and another is 2.111 grams, we are going to get 5.611. Okay, but we have to go back to our numbers and look at the lowest number of decimal places. So the 3.5 only has one digit past the decimal, and the other has 3. So our least number of decimal places, our least precise measurement is 3.5. So we have to round to 1 decimal place. So it's just 5.6.
Excellent. Now we're going to talk a little bit about error. And this really is like in the laboratory. These are errors, and they're not mistakes. Like if you spill something, you clean it up and you start over. What we're talking about is error that's associated with measurements. Now, whenever you make a measurement, there's going to be some amount of error. If you weigh yourself on a broken balance and it always weighs 10 pounds lighter than your actual weight,
Love that
this
balance.
is called a systematic error. Random error is different. This might occur, let's say you're reading that graduated cylinder and your line of sight isn't perfect. So maybe you're holding it a little high or a little bit low, so you're not looking at it straight on. And when you estimate that last digit, it might be a little bit high or a little bit low. That's a random error. Now, when you're doing lab reports, you're often asked for sources of error. So look to your measurements for error. Every single measurement has some error.
All right, accuracy versus precision. So accuracy represents how close to the actual mark you are, what the true value is. So if you take a measurement and it's very close to what is expected, then that's accuracy. Now precision represents reproducibility. So we have these 4 marks here, and the white dot in the middle is, say it's the true measurement. And let's put a couple things up here and let's analyze them. Let's say we take a measurement, we get that, and we get that, and we get that. Okay, now this is not that precise. Every time we take a measurement, it's kind of different. But if you average those together, then you're going to end up being pretty close to the mark. So this is actually accurate without being precise. And this is a random error, and random errors, if you take multiple trials, is the reason we have multiple trials, and you can average out that random error. So moving down, we have a series of measurements here. So this is very precise, but it's not very accurate. So again, reproducibility is precision. So here we have, if we average these together, we're not going to be very close to that mark, and we're also not very precise. And here we have accuracy and precision. So that's what we like. Okay, so I like archery. Here I am with my bow, and I was aiming for the upper center target there. So in the red would be perfectly accurate. So, am I accurate? Am I precise? What do we think? I think I'm precise. There's 3 arrows right there. So I think I was precise, but not quite accurate.
All right, so in this lecture, we talked about significant figures, error, and accuracy and precision. So you need to know how to count those significant figures, and practice goes a long way. Thanks for watching.
See you next time.